All right, welcome. Here I'm going to go over a few example problems or some R code related to some of the types of problems that you're seeing in homework 5. So just a few examples. Again, I'm not going to work through the whole homework set, but give you some prompt to help you get started with that. So let's go ahead and move over to R. And just going to get that open for us so we can check a few things out. And I've already got a data set loaded in here for you, for me. So it's called D5. So I'm just going to go summary D5, and I'm just going to come up here and click run. And I can see that it's got Y, X1, 2, 3. So again, you might do some preliminary examination of your variables, make box plots, histograms. You might check things out for your data set just to get familiar. But what's new here in module 5 is, and for homework 5, is you're looking at heteroscedasticity and some tests for heteroscedasticity. So that's going to involve doing a Breusch-Pagan test. Well, before we do that test, we need to run a regression. So here, let's go ahead and build a model. Linear model, we're going to use Y as the dependent variable. We'll use all of the X's as the independent or explanatory variables. So the X1, 2, and 3 are going to be our regressors here. And data equals D5, we can run this. And we can look at the output, so summary for our model. Maybe we also want to take a look at the residual plots. I think we surely do. So let's just look at the summary, and then I want to get the plot out here for M. So I'm just going to look at the results. So summary for the model, run, and I can see what's going on here. It looks like X1 is highly statistically significant, right? So a very small p-value, large t-statistic. X2, not so much, right? 0.25 is kind of a large p-value. X3 at 0.9, quite large, right? So not statistically significant by any stretch of any imagination. R square, 0.61, so not especially large, but not especially small either. And you can see the root mean square error there too, and so on, the F statistic and whatnot. Okay, so you've got your model there. Now, let's go ahead and look at the residual plots if we're trying to get an idea about heteroscedasticity, and then we can conduct a Breusch-Pagan test as well, but let's just run this out. And what I see over here when I'm looking at the plots, and something that you might be looking for, if you're thinking about heteroscedasticity, thinking about the variance of these residuals. So you've got residuals here, and looking, is that variance constant across the different values of the explanatory variables? And what I might point out here, or what I kind of see, is that if I look at these observations here, these fitted values, it looks like they're not quite as spread out as if I'm looking at these values, right? They tend to be more spread out. Or just to get a different picture on that, I kind of see these things spreading out as the fitted values, that's the Y hats, get larger. So that's just something that I think I'm observing there. So initially it looks like, yeah, I think graphically it appears that there is maybe some heteroscedasticity going on, that the residuals or error terms are not homoscedastic. So when you use a Breusch-Pagan test, it's in this LM test. That's the library. I've already called it before, but so I'd have bptest and the model M, model object. So have that in there, and I just click run, and it comes out with the results for me. Where I'm focusing at this moment is the p-value. So at the 0.05 level of significance, I'm going to reject the null hypothesis of homoscedasticity. Not just barely. I mean, 0.0478 isn't a lot smaller than 0.05, but it is smaller. And so I'm going to reject the null hypothesis at the 0.05 level. It looks like the errors are heteroscedastic, that they have non-constant variance. Now, I might be curious where that's happening or what the cause is. If I've got 3 different variables, it could be that it's not attributable to any specific one of those. But let me just look at some of these. So x1, and then I'm going to look at the residuals. So resid for the model, get that. And then I'm just going to copy paste here. So I'm looking at this for x1. I'm going to look at it for x2. So just change this to 2, and for x3, and just see if this gives me some idea about maybe what variable might be causing this. Just if I can get some idea there, since I've got several variables in here. So run, run, run. And then I'm going to take a look here. And I'm looking at this one for x1, x2, and x3. Do I see changes in the spread of these residuals? So against this axis, it's the residuals, as the x values get larger or smaller. So I'm looking at x1 here, and I'm noticing this kind of thing. I don't want to get too caught up in one observation, right? That's pulling this line down here. But still, if I can look at, it appears that out here, they seem to be fairly spread out, whereas in here, they seem to be less so. When I look over at x2, I don't see quite the same thing. I mean, I can, if I take from this one point and I draw down to there, and I draw out to there, yeah, it does look like they're spreading out. But ignoring just these few observations, right, I don't see, it appears that it looks fairly similar across. Right? I don't see that if I just draw this, maybe if I want to capture those couple of points, but it doesn't look quite as likely to be the culprit as x1 does. And same thing if I look over here, setting aside that top one there, oops, doesn't look like a lot is going on. Maybe a little something. This x1 looks like it might be the main culprit. Just visually getting an idea there. All right, then I'm working up to getting a weighted least squares regression. So I want to find the fitted values. So here I can say, yeah, I'll just say fit, let's say, or fitted values. I could put them in the data set too, the data frame D5 if I want, but for right now, I'll just take these this way. So it's going to be what? Fitted, so I get the y hats, fitted values for the model M. With that, and then I want my weights, I'm going to call it W, and it's going to be, in this case, 1 over, I can say fit squared, do something like that. Or maybe I want it to be in terms of x1. Maybe I think that x1 is the culprit over here. So I'm looking at that graph, and maybe I have my weight be 1 over x1 squared or something like this. I've got some choices, and depending on what problems you happen to see in your version of the homework, you might be looking at some different things, but the idea is to find a weight. Your particular homework problem will tell you the process for that. You can look back to examples in textbook, in lecture, but you're going to get a weight out there somehow. So then to get the weighted least squares regression, so MWLS, let's call it, for our weighted least squares model. So again, we've got a linear model, we've got Y, and whatever explanatory variables happen to be in the particular model that you're interested in or that you're looking at. In this case, we have 3, x1, 2, and 3. And now we're going to add in this line weights. So that wasn't there for previous regressions in the modules leading up to this. And it's W from just line 38 here on the screen. And then data, same thing, D5. Let's see if this will run. It does. Let's see if we can get a summary out here for our weighted least squares model, and if it looks a little different. So if I'm coming back up, let's just note that this has 1.68, 2.66, and so on, whereas this was negative 0.5 and 2.85. So the model parameters have changed. The regression parameters, our estimated parameters, have changed. So the weighted least squares did something, as you might expect, and we've got different values out. Okay, and you can look at these test statistics. You can go from there. Another thing that I want to focus on here when we're looking at heteroscedasticity is getting the what are called white or heteroscedasticity consistent standard errors. So these standard errors that are being adjusted for the presence of the change in the variance for the errors. So we're going to use the sandwich package. So let's just, I've already installed it, but I'll just get this out here. So sandwich, just run that. And then I want to get these standard errors. So there's something called a variance covariance matrix, and the standard errors are the square roots of the values along the diagonal of that matrix. So we're going to look at taking the square root, because it's a variance covariance. So the variances, standard errors are like standard deviation. So it's square root of the diagonal elements of this variance covariance matrix. So variance covariance HC, or heteroscedasticity consistent, is what that's getting at there. And yeah, so then type in the model name. So we'll just go with the model from before M. You could use MWLS here, but, and then we want HC0 because there's some different options. But for this course, so that we are getting the same answers, let's just go with HC0 throughout. Later, you can change that if you think something works better for your purposes, but for this course, let's just use HC0. So I've got this here on this, and it gives me the standard errors for this. Notice that these values are different, even from what the, well, I don't have the ordinary least squares one up here. Let me actually go back up there. So, but let's just pick out X1, 0.259 is what it says. But if I go back up for my ordinary least squares regression, and it's not 0.259, it's 0.313. So the white standard errors are different from the ordinary least squares standard errors. We're getting there. And then we can also get the test statistics with this. There's a, we can use this coef test, which is in the LM test package, which I already had the LM test installed up there. You can see, or called that library. And what am I going to do here? I've got the same model, and then it's got variance covariance matrix that we're going to use. Oops, I need to type that in right though. So you saw I started typing in wrong, would have given me an error message. That's fine. That error message tells me go back and look. I caught it before I hit enter, but that's doesn't always happen. So yeah, yeah. No, I'll get it right one of these days. Just hit enter. And then I'm just going to use the variance covariance matrix that I specified above. So V, C, O, V, H, C for the model M, and HC0 and see what this produces. Okay. And now I've got t-statistics that I can use for hypothesis testing. I can use these standard errors. Note that the standard errors that it's using now, 9.297, this is a match up here. It's a different color. And the 0.259 is the same as this. All right, the 0.2944 is that value. 0.8300 gets rounded. It's this one down here. So you can see that now this table is using, or this output is using the white standard errors. And from there, if you're doing hypothesis testing, let's suppose you have a hypothesis other than that. Let's just go with X1 for simplicity here, or just for this illustration. Let's suppose it's something other than that the coefficient is 0, because for that you get this test statistic here that it reports 11.01. But let's suppose you wanted to test the hypothesis that the coefficient on X1 is something else, like 2. So now you could just put in 2.85338 minus your hypothesized value, so 2, and divided by your new standard error. So let's go with the slightly more detailed version out here, right? And then this is going to give you your test statistic for that hypothesis that you're using, right? So 3.29, right? Different from 11.01. And so that's something you do. So hopefully this helps, just walking through, again, some examples of some things you might be looking at in working on this homework set. Hopefully that helps and gets you going with just getting started with it. And good luck.